or something like this. Yeah. So it's mostly like the homework.
Yeah.
Practical. Yeah? Yeah? Okay. Let's have a look at the homework. Can we see this came out right? Great. I think I should make it a little clearer. Yeah, great. Okay. So let's have a look. Do you have the first question there? Let's have a look. What's the first one? Does anybody have it? Yeah? You're going to open it, Adnan? Yeah? You have the first question? No? Did you do this?
Yes. Yeah, but I don't have the question.
You have the question.
80 kilograms.
No. Yeah. You have it? Do I need to open it here? Do you have it, Adnan, or do I need to open it? Nobody has it. But I thought you took a photo on your phone.
Well, maybe you say don't take
Okay, I'm taking it this point.
I can open it here if nobody has it.
Why not? I'm already on the page.
You're already there? Okay.
Yeah. Number 1.
Great.
A 10-meter helicopter blade spins at 300 rounds per minute.
Okay.
That means it rotates 300 times. Yeah.
So this.
Sorry.
Yeah. 10-meter helicopter blade. Now, if you watch the video from last year, you know, as I had a discussion with the students on if we count this as 10 meters or if I should count this as 10 meters. So I said a helicopter blade, you know, that spins around.
Yeah.
So what do you think? Which are you going to take?
The short.
The short one.
Yeah, maybe short would be better. Okay, so how fast is it?
Why did you take? Why did you take
It's more an English thing than a maths thing. The word blade.
It's just one blade.
Yeah.
Yeah, you see, most people say a blade for only this much of it.
If it's blades, then...
Yeah, maybe blades would be the whole thing.
Yeah.
But I always picture a helicopter blade as being one, but it doesn't matter. It's no big deal. For blade, we mean just half of the total. It's an English thing, not a physics thing. You can, I don't know, maybe you can look blade up in the dictionary. Yeah. Well, how fast is it spinning?
How fast is the blade? Yeah.
Yeah, and what's this? 300 RPM?
300 RPM.
RPM. Okay, so that would be equal to 300 over 60 per second.
5 hertz.
5.
Yeah, 5 hertz, is it?
Yeah.
Great, so the V equals omega or. Is that right?
Yeah.
Yeah.
You'll find
But omega is 2 pi over T, but T is 1 over F. So the answer is 2 pi F or, which is 2 times pi times F times or. What did you get?
340.
314 meters per second. I don't know if that's too fast for a helicopter. Oh no, it couldn't be going this fast. Okay. Right, you got this. This is okay. What's number 2?
A car turns around the corner and the circle forms is a radius 3 meters.
Yeah.
The car is of mass on 1500 kilograms and it takes 3 seconds to turn the corner. What is the centripetal force that allows the car to turn the corner?
T is
3 seconds.
no.
That's, yeah, so
It's now. Don't tell them why. The T is not 3. It's 12. Now Y, look. Here's the corner, and the car comes along here, yes, and then here, it turns. This is only 1/4 of a circle.
Yeah.
Remember, the T is for
The whole round.
a whole circle.
Oh.
So in fact, the T should be 12, because it'll be 3, 6, 9, 12 for a full circle. Now, that was kind of sneaky of me. I did that on purpose. But I wanted to make you remember that the T is for one full turn of a circle. I think most people said 3.
Yeah.
Yeah, at first. Yeah. And what am I asking you for?
What is the centripetal force?
Right, okay, so we have F equals ma, which equals mv squared over r. Do we know the m? Yes. Do we know the r? We do.
Yeah.
Yeah. Do we know the v?
No.
No. So we can say v equals omega r. Do we know the r? Yes. Do we know the m? Yeah. Do we know the omega?
No.
No. So finally, well, why don't I just work the omega out? Omega is
2 pi upon
2 pi over t. So the omega is 0.5236 radians per second. So if I put that in here,
1, 2, 3, 3.
times r squared times 1500. You have it there. What is it?
1216.
Yeah, roughly 1, 2. For me, I got 1, 2, 3, 4.
Yeah. For me, 1, 2, 3.
Yeah, but if you got one, what's say 1, 2, 3?
1216.
Yeah, that's okay. It's because of this one.
Okay.
Yeah. So that is 1, 2, 3, 4 newtons. Yeah. Was that the only thing I asked for this one? Yeah. Was this the same video? No, it's not. Wait, no, that was the video before last one, yes, where one student was very unhappy about this. Yeah. I didn't sound angry in this video, did I?
No.
Okay, it was the year before that, I guess. Right, number 3.
A girl swings a 3-kilogram ball in a horizontal circle.
Horizontal is this way, okay.
Radius 2 meters by a meter string.
Okay.
Take t equals 0.25 seconds.
1 sec, sorry, I'm just drawing this here. So you said that the radius is 2 meters?
Yes.
Yeah.
T equals 0.25.
I suppose if it's 2 meters, it's going around her. Doesn't matter. And t is
0.25.
0.25 seconds.
To travel in one full circle. Find the tension.
Yeah, so it's hard to draw, but what's happening here is maybe it's a rock on a string or something, and she's swinging it around. So here, there's a force in the string, and this force is called the tension force. That's not the same as this T. So I'll just call it F. Yeah? Okay, so we're looking for F here. Yep. Right. F equals MA. A equals V squared over R. Is this the same as the last one?
Kind of.
It is, yeah, because then this would be M omega R squared over R. So I should calculate the omega. The omega is 2 pi over T. 2 pi over T. 25.
Yeah.
Point 13. 12. I got 13. No.
12.
What are you using for pi?
3.34 and
1 4.
pi.
Yeah, I'm using 3.141592654. So mine's a little better. Right. Okay. So we have omega times or squared times the mass. What's the mass?
3.
3 kg, is it?
3789.
Times 3 divided by 2. What did you get? Yeah, it's quite big, isn't it?
3790.
3790 newtons. Yeah, that's fine. 3789. Yeah. Okay. Are you writing this down? Yes. Are you sure? Okay. Is there a 4?
Yes. A girl swings a
Mhm.
3 kilogram ball in a vertical.
Now, okay, so this one is a bit different. This one is actually a bit hard. So she spins the ball around in a vertical circle.
Of radius 3 meters.
Okay.
I mean, the string it says 0.5 seconds, 50 for the ball to travel in one full circle.
Yeah.
Any fine tension.
Okay. What did you say the radius was?
3.
3 meters. Okay. Find the tension at the top
Yes.
and at the bottom.
Yes.
Yeah.
Highest and lowest.
Highest and lowest. Okay. This one, be very careful. So we want the force at the top and at the bottom. So let's look at the top first. So I'll do the top first. When you look at the ball, there are 2 forces on the ball. What are the 2 forces on this ball up here?
One is gravity
One is gravity,
and one is
and one is the tension from the string.
Yeah.
Now this T is not the same as this T,
Yeah.
okay? Tension from the string. The string is pulling, yeah? So in total, the force is mg plus T. Now we know what F is, it's ma from Newton. Do we know the m? Yes.
Yes.
Do we know the g? Yes.
Yeah.
The m? Yes. Do we know the t?
No.
That's what we want. And do we know the a?
No,
No, but we can find the a. So the a will be v squared over r. Yeah. And this is again the same thing. The v equals omega r. So let's get the omega. The omega is 2 pi over t, which will be 4 pi, isn't it? So I got 12.57
Yes.
radians per second. So this will be m omega r squared over r equals mg plus t. So the t is what I want. So the t equals m omega r squared over r minus mg, which equals, let me just multiply this by r.
the mass?
Yeah, what was the mass actually? 3 kg mass as well? Okay. I have 1421 minus 29.43
444.0.
1392 newtons.
Yes.
That's what you got.
And for
I must have mistyped something. I'm pretty sure that's okay. You got the same.
you've got 1390.
What did you get?
And for 4.3.
Oh no, two different. Okay, let's look at when the ball is at the bottom.
Oh.
That's the easy one.
I'd say about the same. So let's look here. Look, We're looking here now. So there are two forces. What are the two forces here? The first one is the weight, yeah. But now the T is going up. So the total force is not mg plus T, but instead it's T minus mg. So this is the same, except instead of plus, it's minus. So the only change I need to make is here is a minus, here minus, here minus, here minus. So here is now a plus, here is now a plus. So the second answer would be 1421 plus, yeah. 1450 is the second answer. So you don't really need to do it again. You just need to change the sign to fix, to redo it.
I did the bottom first because
Yeah.
I knew that it's going to be T minus mg.
Okay, this made more sense to do first. That's fine. Yeah. This was an exam question a few years ago. In the final exam. Did you write this down? One question left? Two. Right. The next one is number 5, is it?
A boy swings a 2 kilogram ball in a horizontal circle.
Mm-hmm.
His hand is above the center of circular motion.
So the boy swings a ball in a horizontal circle.
2 kilograms.
And it's 2 kilograms, yeah. And his hand is above the center of the circle, so it's going around like this. Okay, yeah.
By means of a 13 centimeter string.
Okay, so here to here is 13 centimeters.
So that the motion forms a cone of height 12.
Alright, so this makes a height of 12 centimeters.
And a radius of 5 centimeters.
Oh, I didn't even need to tell you that. But okay, I told you it. So this one here is 5 centimeters. Yeah.
Periodic time is 0.5 seconds.
0.5 seconds.
Final tension.
Final tension. Okay. So here I can know the angle. It's tan inverse 12 over 5. Tan inverse 12 over 5 is 67.38 degrees. Now, if I look at this ball here, there are two forces on this ball. What are they? Weight, which is 2G, and tension here. What should I do with this? Yeah, I should make this one T cos 67.38, and here T sine 67.38. So you can say T sine 67.38, that should equal 2G, yeah. So can this give me T? Yeah, it can. I get for T equals 21.26 newtons. So if I put that in here, when I'm looking horizontally, T cos this will be 8.175 newtons in the horizontal, the T cos. What type of force is this?
Which one?
This one here. What type is it? What's the word? Oh, come on, you couldn't have forgotten it already. It was only Monday.
Centripetal.
Thank you. Centripetal force. So we can say F equals 8.175, MA equals 8.175, 2A equals 8.175, A equals 4.0875. A is V squared over R, and what's the R here? 5, isn't it? 5 centimeters. 0.05 equals 4.0875. So V equals 0.452 meters per second. Now, what was I asking you for? The V, was it, or something else?
No, it's just find the tension of the string.
Oh! I went too far. I could have stopped here. Alright, sorry. That's all I needed to do, was just to hear. Yeah. Well, as a bonus, you know the speed as well.
Okay, so why have we used the sine formula? Because it's in horizontal way. Oh.
What are you asking me?
Okay,
Don't make me sad.
no.
Okay, sure. Because near this side touches the angle,
Yeah,
so
so
that
it will be
makes it the
It will be t cos and the upper one will be sine.
Yeah.
So
We just use the t sign to find the t, and then we subbed it in the t sign to get.
Oh yeah, well actually I didn't even need this. I suppose this is where I should have stopped. It was just a T.
Yeah.
I think I'll change that question, because if you stop here it's too easy. I think I'll change it to how fast is the ball moving?
Keep going.
Yeah.
21.26
Yep.
is the tension.
Yeah.
And what is 8.175?
This one.
Yeah.
This one.
The first horizontal.
Yeah.
21.26 cos 67.
Yeah. Okay, you have this one then?
Yeah.
Mm-hmm. Yeah, so I'll...
Still don't understand.
What don't you understand? Go on.
I think I'll do it, and then I will understand.
Okay, good. Good idea. I agree. Right, 6.
A very small, smooth marble is placed on the top of a very large, smooth boulder. The marble rolls along the boulder and leaves the boulder at what point? The exit angle with respect to the vertical axis.
Great question. Very difficult. A small ball rolls on a big ball until it falls off, of course. I mean, it's not going to stay on it, right? It's going to fall off. So I want to know, what angle does it make at the point when it leaves? Difficult, yeah? Yeah.
I didn't know what to do.
Yeah, so it's a good question because it puts a few ideas in one question. So it's a good question. We'll do it together. I don't give you any information, do I? No. So what we'll say is, we'll call the big boulder, its radius we'll say is big R. So there to there is R, and there to there is R as well. And then here we'll say this is when it leaves. So we'll call this angle here alpha. Yeah. Okay. So, off the ball, there are two forces. What are the two forces here? Gravity, which will be mg, and yes, the reaction force. Now, which way does the reaction force point? It's kind of out here, isn't it?
Yeah.
Along the center.
Yeah.
This is the reaction force. Okay. So, what I need to do is resolve the mg into a component this way, and then a component this way. Now please be very careful. If this is alpha, then which one is alpha here? The left or the right?
Right.
The right.
The left.
Ah, the left. Because if you remember this from high school,
Yeah.
if this one here is alpha, this one here is alpha.
Yeah.
Do you remember that from middle school? Yes.
Yes.
So if this is alpha, this one here is alpha. So this is cos or sine?
Both. This one.
Fine.
And this one here
Both.
is cos. So let me just zoom in. Here's the ball, and this way we have mg cos alpha. This way we have or, and this way we have mg sine alpha. Yeah? Yes?
But why did you take mg cosine alpha? Why?
Why did I do this basically? Good question. The reason is because this is moving in a circle. So I want to know how much force is going to the middle. This mg, it's not pointing to the middle. I need to break it into this part and into this part. And this is the part I care about because it's going to the middle. When it moves in a circle, we want to know how much is going to the middle. The name of this force is centripetal force. This is what I'm trying to get, the centripetal force.
But why do we use the weight instead of the reaction?
Because the reaction is already pointing to the middle. So I'm happy with the reaction. But I'm not happy with the mg because it is no way pointing to the middle. I need to know how much of it is directed to the center and how much of it is not. It's a bit like with the turning force. You remember the turning force? We really care about how much is perpendicular, not how much is to the center. This is like the opposite. Here we really care about how much is to the center, not really the perpendicular. So when you look at these three forces, which two forces do you care about? Which two do you care about?
mg sine and cos.
No.
Cos.
No, I care about mg cos and the or, because these two together go towards the center, which makes it turn in a circle. I don't really care about this just yet. This is the centripetal force.
Yeah.
In other words, the centripetal force is mg cos alpha minus or.
Yeah.
This is the centripetal force to the center. Now I'll just pause for a moment. Are we clear on that or not?
Okay, again, why did not all mg cos?
Because the mg is pointing to the center and you want to know how much force is going to the center. The or is taken away from that. It's a bit like in the last example with the rope, with the girl, where she gone here. You care about how much is going to the center. So here both the T and the mg go to the center. You add them together. But here only the T goes to the center and the mg we take away. It's the same thing there. No, I need a question.
I think that's why you take mg cosine alpha minus.
Which is pointing to the center? This one or this one? Which is pointing to the center?
mg.
Yeah, so this is the one I want, and this one is making this smaller because it's pointing away. So this is the one I care about, but this one is pointing away, so that's why it's a minus. It's reducing it because it's opposite. Is that a yes or a no?
Yeah.
Are you sure? You look confused as well. Is this just a natural look or why? Are you sick?
No.
No breakfast?
I don't do that.
Terrible. Right. Okay, so can I continue from here?
Yeah.
Yeah. Now, the F, that's equal to MA. Thank you, Mr. Newton. And the A
He's got
over OR, big OR. Oh, rats, I shouldn't call it big OR because I'm using OR here. I'll call it small OR, okay? Yeah. MV squared over R equals MG cos alpha minus 1. Okay? Now, I can get here MV squared equals MG OR cos alpha minus OR.
You multiply by R?
Yeah.
Yeah, yeah. And I can say a half MV squared equals a half MG OR cos alpha minus a half OR. I multiply by a half.
Why?
Yeah, why did I do that? Why on earth would I do that? Why?
Balance.
It was before.
Still balanced.
Yeah, it's still balance.
Can you take a
Thank you.
Oh, okay.
So I have kinetic energy equals a half mg or cos alpha plus a half or. So this is one equation.
It's minus.
Oh, thank you, minus. Okay, can I make another equation with kinetic energy? I can, because I can say at the top, what energy do I have? Potential energy. And here, what energy do I have? Kinetic energy. So if I can just zoom in for a moment here. This is alpha. This is OR. How big is it from here to here? And remember, this is OR as well. Here to here? Oh, come on. No, come on. It's a triangle.
Sine.
Oh, cos. This is OR cos alpha. Of course, isn't it? So how much is it from the top to the bottom? It's OR plus OR cos alpha. From here to here is OR. Yeah? So on the top we have what type of energy? Potential. And here, potential plus kinetic. So on the top I have mg, and what's the h? The height? No, at the top. 2r. And that should equal mg, and what's the height here? R plus R cos alpha. Plus, what other energy does it have here? Kinetic energy. A half mv squared. So you can say a half mv squared equals 2 mgr minus mgr minus mgr cos alpha. I just take this over to the left and I open it. So here I get kinetic energy equals mgr minus mgr cos alpha. So mgr 1 minus cos alpha. This is my second equation. Please write this one down. Now you can... No, but I told you it was hard. It's not a shock. This question came with a warning at the start. I said, it is very difficult. Yeah? So you were warned. No, but these are great questions to improve your understanding. You know, and to put several ideas together. Yeah? Yeah? Okay. Right, so what we're going to do next is put the two equations together.
So it would be more harder.
No, it'll start to get simpler now. Yeah. Okay. Did you write
2 mgr?
2 mgr minus 1 mgr. Okay.
Can you show me that now?
My ugly diagram here.
Okay.
You got this? Can I go back to the right?
Yeah.
I can get it from the video. Yeah, need to move on. Okay. So what was my second formula? It was KE equals mg or 1 minus cos alpha. Great, so we can make these equal, can't we? Because they're both equal to KE. So we get a half mg or cos alpha minus a half or equals mg or minus mg or cos alpha. So what I'll do is I'll take this to the left and put it with this one. So we get 3 over 2 mg or cos alpha equals mg or plus a half or. Now here comes the key step to solving for alpha. If I go back to my picture, what is special about the point when it leaves the surface?
No potential.
No, so that's potential. Look here, look.
Only
When it leaves the surface, something changes here when it leaves, after it exits.
it's only mg force because maybe like no reaction force.
Very good. There's no more reaction force when it leaves. Why not?
Because it's in the
Because it's
gravity.
It's not touching it anymore. So at the point when it exits, when it leaves, the ore becomes 0. And this is what we want, this point. So, what do I make the ore here? 0. So when it exits, when it leaves, this is gone. Mg ore is here, Mg ore is here, so I can cancel. And I have cos alpha equals 2 over 3 when I bring the 2 up and the 3 down. So finally I can get the angle at which it leaves. 48.2 degrees. This is the exact angle when the marble falls off the big boulder.
When cos will go that side, it will be inverse. Cos inverse.
Yeah, I did a cos inverse. Yeah.
So all of this at the end is got theta equals 0.
Yeah. But this is a good thing. This is what you want in physics.
What is the given here? Given.
What's given? Nothing.
Nothing?
No. All I said was you have a big ball and you put a small ball on top and you let go and it rolls down and falls off.
We're just playing with the ball.
Yeah, that's all. Yeah. Now, I don't tell you the radius of the big ball, which means that it doesn't matter what it is. If it was 1 meter or if it was 2 meters, it will still leave at the same angle, because I never told you what the radius was here, did I? But did you need to know it? No, which means it's not important. You get the same answer. Yeah.
Even if like if both of them move, so obviously like
Well, if both of them move, it changes then. Yes.
no, sorry, like if both of them got different R, but like the same R, that's gonna be the same. But one of them was only one of them changed.
Now, what I'm trying to say here is that it doesn't matter what this radius and this radius are. If I make this bigger or smaller, the angle it leaves will still be the same.
If we only make one of them bigger or smaller, will it still be the same?
Yep. Oh, you were thinking if we kept the proportions the same. Yeah, no, like if this was 2 meters and this was 1 centimeter, and I change this to 3 meters but keep this 1 centimeter,
Yeah.
Same answer. Yeah. Not only that, if you look at my answer, you notice that this answer has no or. Also, it has no G in it. Which means, if you did this on the moon,
It would be still
it
the same.
still would be the same.
But there is no gravity.
Less gravity.
Yes.
It would still be the same
Like
answer.
Like you will feel that you are flying.
Yes. but the answer's still the same. And I just think that's amazing that you've shown that no matter how big or small it is, if you're on the moon, Earth or Mars, the answer is always 48.2. Yeah. Now I said it was a difficult question, but I think it was worth doing to see this.
Yeah.
You know? And you have two ideas in this. You have the force and also the energy as well. You need to put both of them together. Okay. It's a good question. It's a difficult question. We'll go on to the next lesson now. I don't know if you just want to write the last part down here where I get the answer. So 48.2. No.
Yeah.
No. But I still think it's a good question. It is a good question. It is. It is. Okay. Did you write this down? Yeah. Well, it's in the video anyways if you want to. So let's have a look at the next lesson then.